I'm a member of this area of excellence since the beginning. I'm also a professor of physics at McGill University in Montreal in Canada. So today I will actually chair today's session. Our first speaker is Professor Gabriel Aeppli, who actually visited us, I think, last year, and as in the capacity of our advisory member, committee member. And today he will tell us about controlled quantum states of isolated interacting defects in silicon. Of course, Gabriel is a very well-known researcher. He won many prizes, including the, I think, 2005 Bucky Prize of American Physical Society, and he's a member of Royal Society of London and APS Fellow, and so on. So we are very grateful that he will be here to give us a 1.5 hour extended lecture. Thanks.
Thank you very much for inviting me to this very nice workshop. It's also an absolutely beautiful day today. It's really seeing Hong Kong at its best. It's very nice that the organizers were able to manage that. I'm also very honored to have so many friends in the audience, and including of course, long-standing friends like Kuchun, but also more recent friends like yourself. And I have to also say that the work that's being done here in Hong Kong on the device modeling is really of large interest to us, and I think will impact not just the work in traditional devices, but also in quantum devices, which is the subject of this talk. So what I will discuss today is the topic that was just advertised, controlled quantum states and defects in silicon. Here are some of our recent papers, which I'll try to highlight during the talk after I've given a bit of introduction. But first, I just want to say that the work I'm going to be talking about is a result of a collaboration with many people. Can you hear me, or is many people, both in London, but also at the FY in Utrecht, which was recently moved to Nijmegen. People at Surrey, up in Scotland, and even in the Highfield Laboratory in Florida. So certainly what we've been doing would not be possible without all of these participants. I've left out one participant who will give a separate talk on a new aspect of this work, and that's Brian Billis, who's sitting there. He'll talk about using MOSFETs as detectors of orbital states in silicon. So let me just, with this audience, I hardly need to show this slide, but I'm going to do it anyway because I can always just remind you why we're here. This is computational power as a function of time, and this is calculations per second for $1,000. This is 1900, and we were doing about 10 to the minus 5 calculations per second for $1,000. So that $1,000 actually didn't buy you very much then. Today, we're up to doing something like 10 to the 10 calculations per $1,000, or 10 to the 7 calculations per second per dollar. This is a 15 order of magnitude increase over the last century or so, And you're used to seeing Moore's law plotted as an exponential. Actually, the growth in computational power, if you go across the different technology transitions we've had since 1900 between electromechanical and relay and vacuum tube and transistor integrated circuit, actually that has actually caused this super exponential increase. Interestingly, actually, the integrated circuit is really the longest lived technology on this plot. And the reason it's been so long lived is because it's essentially been two-dimensional and it's been planarized, essentially relied on our ability to simply keep making the same basic device just smaller and smaller with each succeeding generation of fab, particularly as we've steadily improved optical lithography, improved gate dielectrics and everything else to make these objects generally thinner and smaller in the lateral dimension. So that's driven this tremendous advance or this maintenance of the exponential growth and super exponential growth in computing power over the last 50 years. Just keep decreasing essentially these design rules, and we keep improving our chips. Now, this has been going on, as we know, for a long time, and many people are now saying, well, we're going to be facing the end, somehow the end of this bit of Moore's law, the most recent bit. And here are a few things that people talk about when they say that this is just not going to work as well in the future as it has in the past, that we need to undergo another one of these transitions that actually were subsumed in the previous slide, the transition between transistor and integrated circuit, or between vacuum tubes and transistor. Here's one. This is showing, again, the design rule. This is actually from left to right. This is big and this is small, and showing essentially the power that's dissipated per square centimeter. Just to give you some scale here, we're sort of we are actually in the region where the power densities are similar or even higher than that of panini toasters. Eventually we'll be hitting power densities, just on straightforward extrapolation, similar to those at rocket nozzles or on the surface of the sun. So that's a problem. It's a thermodynamic problem. There are cost problems as well. The risk that you assume with each succeeding generation of fab seems to be larger and larger, even though the cost per transistor is going down. So you're sort of betting $1 billion or more on a high-end fab these days. Eventually, be betting $10 billion or $100 billion. That's getting to be a lot even for a company like Intel, which I know is represented here today. From a physics point of view, what we find interesting is that we're switching fewer and fewer electrons per device per clock cycle, and as we, of course, the electron is indivisible. Unlike the dollar being multipliable, the electron really is a physical limit, and we're not going to really be able to switch less than electrons per device per clock cycle, at least not in any foreseeable future. And so there's a physics limitation to just constantly making devices smaller and thinner. So this has sort of led to a lot of people saying, this Moore's law is going to be over, this phase of Moore's law. I'm just itemizing again these things that I just described, which you're no doubt very familiar with. And that really leads to the challenges that we face as engineers and physicists, and this is, of course, the reason that we have this marvelous program in Hong Kong on computation, and the reason we're having this workshop is really ultimately how we're going to continue Moore's law for computer and telecom performance brought out an acceptable price. Of course, many people think about that. We have the semiconductor industry roadmap. And really, the semiconductor industry roadmap, of course, now is starting to also talk about not just straightforward extrapolation of the current dominant paradigm, but to go around the physical limits set by extrapolation of current paradigms. You really need one of these paradigm shifts to keep that curve going that started in 1900. And this leads us to consider new types of computing. These types, although I'm going to oversimplify as I've been doing for the last 5 minutes or so, I'd say there are really two basic approaches. The one is really to start doing biology. Of course, this shows you the transistor for 90 nanometer process. This shows the influenza virus. This thing is roughly the same size as that thing, but everybody will agree that this actually can do a lot more calculations on its own than this thing can. This is a much more powerful information processing machine than this thing. So this is one approach. Maybe we study biology, we can study molecular biology and biology, or we can study the brain and learn a few things from that. And perhaps design computers taking those ideas in the future. The other approach, which I'm going to talk about, and which really this project here is about, is to dig deeper on the physics end. And of course, what many people are thinking of doing is replacing classical bits by quantum bits. So why would you want to do that? Well, classical bits, of course, just are binary. They're 0 or 1. And of course, quantum bits, basically quantum states, which correspond to these classical bits, of course, form a Hilbert space, a vector space, spanned by by basis set, which corresponds to the two classical bits. So this is essentially a block sphere. This is just the North Pole and the South Pole of the sphere. So there's a lot more information content there than in the classical case. And of course, it's stored in the same space because a switch is either on or off. But if that switch were quantum mechanical, it would suddenly store essentially the location of the wave function as defined on the block sphere. So there's enormous information potential for the reasons I just described. Quantum states also, as you know, evolve together due to entanglement. So when you have interacting quantum states, then there are Hamiltonians and there are operators, and as they correspond to these states, as the states evolve together in very non-trivial ways, and in naturally parallel ways because of entanglement. And so the question is, why don't we have quantum computers today? The reason is, of course, that something you all learned in school. It's really the Heisenberg uncertainty principle. Quantum states are very fragile. They can break. Information gets lost just if you look at them. And there are many things looking at quantum states in your average material. There are all kinds of spectators, essentially, which cause decoherence. Particularly if there's an intrinsic contradiction between manipulating a state, having the ability to reach in and change a quantum state, and actually trying to look at the, trying to maintain its coherence. Because anything, by manipulating a state, the environment is reaching in, touching that state. Of course, when you're trying to, then the fact that you are able to do that means that there's probably always something slightly touching that state causing it to decohere. So there's a contradiction between gates and coherence in general. That's essentially the challenge that this field has been facing. Now, because of that challenge, people have proposed many candidate qubit hosts. Of course, you know that in classical computing, essentially the host for classical bits of choice is silicon, occasionally maybe some more exotic semiconductor, but generally it's silicon. And that's been agreed upon for a long time. It's argued that the integrated circuit, it's not just argued, it's a fact, the integrated circuit industry was really only took off when silicon was decided to work with silicon. There aren't too many germanium-based integrated circuits. With quantum computing, where classical computing was 50 or 60 years ago, we haven't chosen silicon yet. And in fact, there are many different systems that people are looking at as qubit hosts, including like the magnets on lots of 3-5 semiconductors. There's been a huge amount of progress, especially in the last 2 or 3 years, on superconducting devices, various kinds. But there are also exotic materials like hydrogen heavy centers in diamond. And last but not least, atomic physics has given us atoms and ions in traps, both magnetic, electrostatic, magnetic, and laser traps. Atomic physics has been actually probably the most successful in dealing with this problem, or this kind of intrinsic contradiction between state manipulation and decoherence. And actually, last year's Nobel Prize was given to atomic physicists who made beautiful images. For example, here, this is Lyman and Baroche of actual ions in traps interacting quantum mechanically and producing something here that looks remarkably like some kind of a charge density wave in a 1D system. But they're able to do this in traps. These are essentially images of individual ions. They typically steered around with lasers and various microwave fields. These systems are extraordinarily robust because you're operating with atoms in vacuum, and the only thing they interact with is electromagnetic waves, which you can shield against and at the same time control with exquisite precision. Efforts to do this well in solid state really haven't gone quite as far, but are starting to get somewhere in the case mainly of superconducting circuits. But those superconducting circuits are actually rather large, and there's still quite a ways to go in terms of large scale integration. And so I think the question still remains: if we can't do ion trap physics or ion trap science in a solid in preparation for building some kind of quantum computer based on a solid. And as I said before, these options of solids include a variety of solids as well as diamond. But what we really want is a common solid, which we know how to process. And that leaves only one choice, and that is silicon as a host. That's a question can be reformulated, saying, is there anything in silicon that would allow us to do ion trap physics? And just to remind you again, don't be reminded, there's silicon. Of course, there's something very much like a trapped ion in silicon. This is the dopant. And of course, the dopants are either acceptors or donors. Donors here from column 5. And what I'm going to now spend the rest of the talk dealing with is how actually silicon, the way we know it today, actually is an extremely good ion trap, and actually it may be such a good ion trap that at least at low temperatures we can conceive of silicon as being a basis not just for classical computation as we know it today, but quantum computation in the future. So here's a brief outline talk, giving you the introduction, a bit more introduction in a few minutes. We'll talk about spin manipulation, and then orbital manipulation using light, and then orbital manipulation using electrical fields. So let me start just with very elementary solid-state physics, I think probably 30s, which will essentially be the principal knowledge required to understand the rest of the talk. So how does this ion trap work? So we take the donor, which is phosphorus, which, as you know, has one spare valence charge and one spare, with a spare electron with a valence charge and a spin. Of course, the other electrons just bond, the other four outer electrons just bond to the silicon atoms, just as if the phosphorus itself had been a silicon atom. And this remaining electron satisfies a Hamiltonian, just like the hydrogen Hamiltonian, except that the effective mass that replaces the free electron mass now of the free electron mass vacuum is simply the conduction band effective mass, and that's 0.3 free electron masses. And the Coulomb potential is renormalized by the dielectric constant of silicon, which is quite high, which is 11.4. So the envelope function for these electrons bound in silicon, bound in this vacuum, essentially come straight out of a simply renormalized hydrogenic wave function. And if you look at this, if you now look at the outcome of the core model, there are two key parameters that define the ground state of the system. One is the Bohr radius, which is the extent of this wave function, and the other is, of course, the Rydberg energy. The Bohr radius scales like the ratio of the dielectric constant to the electron mass. So if you just simply plug in numbers, you say your dielectric constant is renormalized by an order of magnitude, your effective mass is renormalized by a factor of 3. You see then that the Bohr radius is 30 times larger for donors in silicon than it is for hydrogen in vacuum. There's an even bigger renormalization of the Rydberg energy, which scales like the mass divided by the dielectric constant squared. And that means that your Rydberg energy is at 70 millivolts. So what you have then in this ion trap are actually giant hydrogen atoms with a lowish ionization energy. So there's really nothing else is happening. And just to give a picture of what this means, here's silicon. And here is your ground state, your 1s state of impurity. It's huge. And what's interesting here is this 2 nanometers. The diameter of that is comparable or is just slightly below what you can do with EV lighting. So this is really no longer an angstrom scale thing. This is really a mesoscopic object. Now, this is all stuff that you've seen in textbooks. A few years ago, we set out to ask, well, how do we know that the textbook is correct? And the way you can check is by doing STM, scanning tunneling microscopy. Here is bismuth doped silicon. Bismuth, again, is column 5, just like phosphorus. I've doped a silicon 100 wafer with ion implantation. And what I'm showing at the top is a simple STM topograph taken at -2 volts. And what I show here are CITS vector, again taken in the valence bands. And what's interesting about this CITS spectrum here is that although I see nothing in topography, there's an object here, actually a rather large object, which is producing an enhanced density of states at -1.3 volts, and a suppressed density of states -1.7 volts. In fact, I can park my tip there and simply look at the difference between the DIDV that I measure at the center of that spot and elsewhere, just on the unperturbed surface, and I get essentially a classic phase shifting resonance. So there's an object that's scattered below the surface of this dope crystal, and it's not associated with any topographic feature. The only thing that I did to this crystal, mind you, was dope it with bismuth. There's nothing else there. And so if I measure actually the radius of that object, that scattering object, the thing that's scattering essentially valence electrons, that size matches precisely the back of the envelope calculation I just showed you a few minutes ago. What's going on here is in this experiment is essentially a depth profile version of the classic Eigler experiment, where he actually showed at the surface of the crystal what happens to electrons which scatter from impurities which he put on the surface. What we're seeing here is we have impurities which are put below the surface. So you have to imagine actually the scattering taking place not on X and Y, but on X, Y, and Z. So this is simply, if you wish, a three-dimensional version, or if you wish, a topographic version of the classic Eigler experiment. Of course, the outcome is this phase shifting resonance. So, a question, of course, that one asks is this is fine. This is one impurity. What happens to these impurities as they approach the surface? This has both a scientific interest, but also a very profound practical interest, because at the end of the day, if you're going to want to read out individual impurities, as you would in a typical quantum computing scheme, these impurities have to be reasonably well behaved, close enough to the surface so that you can actually read out something like an orbital state or a spin state. And so we've actually collected a lot of data on bismuth impurities in near silicon 100 surfaces. In fact, the first experiment which we did, which we now actually published, is bismuth just at the surface. And what we did here was we actually collected a lot of copper graphs and occasionally found this type of feature. And what this is, it turns out, is this is looking in the production band. This is the field states. This is the valence band. And you'll notice that there's actually a defect here. And in fact, what that defect is, you can verify by modeling, actually just density DFT modeling, to be essentially a pair of atoms. One is bismuth, and the other is the absence of an atom, which is a silicon vacancy. So I have a classic 2x1 reconstruction of silicon, where I have these silicon dimers oscillating like that. And one of the dimers, in fact, has been replaced by a single bismuth atom at a vacancy. And this is the side view. And this is this is another. This is a top view and the side view. Now, what about the electronic state of this bismuth atom? And here I'm showing you the IDB curves, just in the tip part of the bismuth atom. And this shows essentially just the silicon by itself, which is the blue curve. You can see that if I look at that bismuth atom, which is the bismuth atom in this pair with the vacancy, actually you see that there's a state in the gap. And actually, what we realized is that to actually understand these data, you need to go to spin polarized to spin polarized DFT rather than unspin polarized DFT. This is what we see for this bismuth atom. So if we have actually if we have no spin, then in fact that state will be pinned directly at the Fermi level, whereas actually if you have a spin, it splits, and we actually get the state slightly below the Fermi level. So what this says is we have actually in silicon, at the surface of silicon, the potential to have a half-filled spin-carrying impurity. In this case, bismuth. For the lighter impurities, this does not happen. Actually, the phosphorus does not carry. Phosphorus actually, you get the correct answer with unpolarized density states calculation. So that's interesting. That it leads one also to imagine, of course, using bismuth on silicon surfaces to create all kinds of artificial two-dimensional solids, which would then be actually subject to the Hubbard model rather than just to some simple mathematical calculation. Now, I've showed you two limits now. I've showed you the deep limit where there's a scattering center below the surface, and that scattering center pretty much matches the Bohr atom. This is very, very different from a Bohr atom. This is a much smaller object than the Bohr atom. It's simply a surface state associated with a surface defect. What happens as I pass between those two limits? So this shows what happens. So this is a zoology of such defects you can see with STM. And this shows the various assignments that we've been able to make based on looking at these pictures and doing some calculations. Of course, what I just showed you at the beginning was type A, which is a visible vacancy pair. Turns out that as you actually go to deeper impurities, actually these patterns become bigger and bigger, and actually as they get bigger and bigger, not surprisingly, you get more and more something which looks like a Bohr atom, although very interestingly, of course, you see that there's actually an underlying cubic lattice symmetry. It's not a spherical vacuum that we're talking about. Like a real vacuum, it's a cubic vacuum. And so these are the various objects as we go to deeper impurities. We get bigger patterns. The other thing that you see is that as your states evolves. So when I look at type A, of course, there was a state in the gap. It was not a scattering center. On the other hand, if I look at type D, which is not as deep as the first impurity, but almost as deep, you're seeing actually that there's really not much of a state in the gap anymore. It more or less coincides with the upper edge of the valence band. And as you go between these, you see this extra this feature just going into the valence band. You can see this in a prettier way by looking at these CITS data presented as a function of distance perpendicular parallel to the silicon diameter and as a function of bias voltage. So here's my defect. Here. Okay. And here's my defect of type B, type C, type D. And what you can see very clearly, if your eyes are sharp enough, is you can see that the defect of type A is actually is confined, has an effect on the density of states, which is actually confined essentially to a single atom. As I go to these other defects, actually the perturbation spreads out, and for defect C and D, the perturbation on the actual density of states is really largely at the conduction and valence band edges. And I see effects of the defect, subtle effects actually extending out over longer distances. If I fit these perturbations with exponentials, I can get an effective radius for the defects. And I can see that as I change the type of defect, the radius actually approaches that of the Bohr atom. This is radius that I showed before, was of course the diameter of this one meters. As I change the type of defect here, I see that the bias voltage at which the bounce state occurs also goes down and eventually just goes into the valence band. So we have really now a very nice, at least qualitative understanding of how impurities, as they approach the surface, make a transition from essentially a nice Bohr atom to a rather special defect, which simply deduces new electronic states rather than just scatter the surface states that were mainly sensitive to the Westian. Okay, so well, I think I went through this to demonstrate that this 1930s picture that presumably all teach to your undergraduates is in fact correct. It's amazing that it's taken at the beginning of this century to actually show that with images. So I said there's of course these extra electrons that the donors come with have both spin and charge. So I've talked mainly about charge, or only about charge. Let's talk about spin. Now, actually, to see spins on impurity, people have been doing magnetic resonance for a very, very long time. Magnetic resonance techniques are very simple to understand. You typically have a microwave source, and when the microwave energy is precisely equal to Zeeman splitting, you get resonant absorption. In that way, you can see that there are spins with a particular G factor in your substance. So, I'm just going to show you an EPR experiment, actually, that we did on bismuth and silicon. Just talked a lot about the bismuth and silicon OSTM, what happens for electron magnetic resonance. So, it's easier to change field rather than to sweep frequency. So typically, experiments are done with a fixed resonator where you sweep field. And what I'm seeing here is not one resonance as I was expecting, but in fact, we can count them at 10 rather than one. But we thought this was a spin and a half electrons. So where do all these extra resonances come from? Of course, they come from the fact that bismuth is a rather heavy atom. It's got a complicated nucleus with actually a nuclear spin of 9 halves. So it's pretty simple then to realize that you can get 10 levels from a nuclear spin of 9 halves. And this is the Hamiltonian. And the Hamiltonian can take terms of the Zeeman frequencies here. And this is the hyperfine coupling, just in megahertz. This hyperfine coupling is actually quite large. There's one important detail which you may have missed. Normally you think that, well, if I just have this term here, and I fix my electron spin, I should just see some kind of Zeeman ladder with equally spaced resonances, which I can find basically by sweeping frequency or perhaps by sweeping magnetic field. These resonances are actually not equally spaced. You see that they're more close to each other at low fields, and they get further apart at high fields. And you might ask why that is. And that's something, again, you probably teach your students in undergraduate quantum mechanics. The reason is as follows. Now, in the zero field limit, of course, the total angular momentum, which is the sum of the nuclear and electron spin angular momentum, commutes to the Hamiltonian. Okay, so what that means is that essentially there are two levels, two manifolds of degenerate states, one with a total angular momentum of 4, and the other with a total angular momentum of 5. And of course, the 4 is just simply 9 halves minus a half, and the 5 is just simply 9 halves plus a half. Okay, so that's what you get. On the other hand, in the limit where the magnetic field goes to infinity, you also get two manifolds. But here, the two manifolds are labeled by the total as Z, okay, which is just the electron spin only. So the SZ, of course, can either be plus or minus a half. And of course, if that then just acts as a field, you can then ignore all this, and that just simply acts as a field on the nuclear spin. And then you should just actually get evenly spaced levels, where, of course, the level spacing is just 1 by 8. And let's just see how that works out. When you do a calculation, of course, you can calculate by hand how you go between these two limits. Let's see how that works out when you compare experience theory. This shows bismuth basically at low fields. Now, at low fields, you can see here these two manifolds. This is the F equals 4 manifold, the total angular momentum 4, total angular momentum 5. And what we're doing, of course, with the microwave experiment is we're putting a ruler on this thing and simply connecting the states of the two manifolds with a ruler which is precisely equal to the microwave frequency. And if you study this, then you can see that because of this bunching, and because both of these levels are becoming degenerate at low fields, you get a higher density of resonances at low fields than at high fields. And in fact, if you go to very high fields, this is where I went to the National Magnet Lab, fields of many Tesla. In fact, you can't see that curvature anymore, and everything, of course, is evenly spaced. Okay, so we're going to get back to that in a few minutes. Just keep that in your mind. So these are now just simply nuclear spin levels. You see, essentially just the 10 lines evenly spaced, because out of these fields, the rate of advancement of these eigenenergies is just simply linear in the magnetic field, given precisely the same slope for all levels. Okay, so that's how we detect spins, both electronic and nuclear, in these ions in basically this ion trap of silicon. What about decoherence? For that, we have to go to the time domain. There are really two decoherence rates. One is the classical T1, spin minus relaxation time. The other is the quantum mechanically interesting one, which is a spin phasing time. And these are best really defined in terms of the block sphere. You have your states, okay, all possible coherent superpositions of up and down, which live on this sphere, or we can write them out algebraically in this conditional form. And decoherence, in the quantum mechanical sense, really refers to the fragility of states that live not at the North Pole or the South Pole, those are the classical ion states, but states that live, let's say, on the equator. Okay, so the way we measure sort of decoherence times and spin lattice relaxation times is with pulsed electromagnetic resonance. So it works just like the CW resonance that we did before, but now we actually do time-dependent, we solve time-dependent master equations rather than just looking at the static solutions for Hamiltonian, as I showed you a minute ago. You take the system, you prepare it, let's say, at the South Pole. Let's say you're at some temperature where the population would really like to be at the North Pole, but you then put on what's called a pi pulse, which takes the population to the South Pole. So you invert the population. And then you wait a while, and you let the population recover. And you measure this recovery of this population essentially simply by measuring essentially the reappearance of essentially a normal spin echo response. And this shows how this integrated, how you basically recover the normal spin echo response as a function of time after such a pi pulse. And this is actually quite extraordinary. So this is bismuth and silicon, and we did nothing special for the silicon. And it's also not a particularly low temperature. This is 10 Kelvin. This population recovers on a time scale of order of 10 milliseconds. You have a T1 time of 10 milliseconds. So in silicon, actually, the classical relaxation time for spins is very long, and of course much longer than the cycle time for any kind of even conventional classical electronics. So that's interesting. And by the way, it's much longer for bismuth than it is for phosphorus. Now, what about T2? So how do we establish that? That we establish by doing an actual echo experiment. The spin echo experiment is illustrated here. Let me just start the slide again. I take the system now and start at the North Pole, but take it to the equator with something called the pulse. And after a while, the system evolves basically on the equator, and I apply a 180-degree pulse. And this thing is actually going much faster on this projector than I've ever seen it go before. Usually I can talk about as fast as it can go. Let's see if I can stop it. Yes, I can. But the basic principle is that you prepare a quantum mechanically interesting state here, you let it relax, and then you refocus it with a pi pulse. And then as the system dephases, it continues to dephase, though, in a direction which is opposite from the direction in which it dephased originally. So after time t, which is precisely equal to the time between the original pi over 2 and pi pulses, you get essentially radiation, stimulated emission coming out of the receptor. So you see emission of microwaves actually after any microwave pulses have gone. So this shows you, of course, to then measure the dephasing time, t, you simply look at the rate of decay of the echo as a function of the time between the pi over 2 and the pi pulse. And this shows the actual data. So here's my pi over 2 pulse, my pi pulse, here's my echo, and this shows the echo intensity as a function of time, this delay time. And you can see that for bismuth phosphorus, and now this is again at 10 Kelvin. You're actually seeing decay times, which again are of order now a millisecond. They're order of magnitude smaller than the T1 times, but still amazingly long for a sample that we haven't done anything very special to. It's an isotopically mixed sample, and it's at quite elevated temperatures. So these quantum states actually survive for an amazingly long time in this conventional semiconductor. An extremely important demonstration, actually, of the existence of the Bloch sphere in the first place, and the demonstration also of control of where you are in the Bloch sphere is Rabi's experiment. And you can do Rabi's experiment very simply with a resonance spectrometer by varying the length of the original pi over 2 pulse. And you can do either vary the length of that pi over 2 pulse, or you can also vary its amplitude. And we did both on this slide. If you vary the length of the pulse, you see these famous Rabi oscillations. Now, why is it that you see oscillations? Well, I said before that you were operating on a sphere. And, of course, a pi over 2 pulse should be equivalent to pi over 2 plus 2 pi n pulse. And so if in essence, I start with a pulse, let's say, which has the length of a microsecond or so, if I then change the length of that pulse, if I then change the length of that pulse and make it, let's say, 5 microseconds long, then I should come back to the same place because I just come around the sphere once more. So seeing these Rabi oscillations is crucial. Now, the other thing that comes up with this power dependence is that, of course, what matters in quantum mechanics is the action, not the power that goes in. The action is actually the integral of the amplitude of the applied perturbation times the time, not the amplitude squared. And you've actually check that by showing essentially that these oscillations, which I'm showing you here, power attenuation, you can convert that into an amplitude, and in fact, the amplitudes. What matters here is what determines the period of the oscillations is the amplitude, not the amplitude squared. And of course, by going to intermediate locations on these Bloch oscillations, you can put, of course, the spin system not just onto the equator, but also at other points, on various other latitudes on the Bloch sphere. So you have control over all of this. Okay. A few minutes ago, I talked about the nuclear spin as well as the electron spin. We can manipulate both. And we can do experiments where we mix RF pulses to manipulate the nuclear space. This works, of course, particularly well at the high fields, where I've cleanly separated the magnetic and nuclear degrees of freedom. And so here, what I've got is a combination of RF pulses and microwave pulses. So this shows the RF resonance corresponding to the hyperfine nuclear split. And I should emphasize here that RF pulses, of course, are a good deal longer than have to be a good deal longer than the microwave pulses because, of course, the coupling of magnetic fields to the nuclei is substantially weaker, and the coupling is 3,000 times weaker than to the electrons. Now, that's actually a bit of a problem if you want to use the nuclei in some kind of quantum computation scheme in addition to the electrons. And very recently we just published a paper where we showed a way to get around that problem. And actually the way to get around that problem is to go into the low, this is somewhat counterintuitive, to go into the low field regime, especially that low field regime which is close to where you see essentially the crossover from the zero field limit, where you have essentially two manifolds with total angular momentum 4 and 5, the high field limit where the good quantum numbers are the nuclear and electron moments IZ and SZ along the z-axis. And what you take advantage of here is that near the place where the hyperfine coupling is close to the external magnetic field, which is here right around the 3/10 of a Tesla. You actually get one of the levels actually that coming down from the upper manifold to join the lower manifold in the high field regime. And so what you see then in the PR spectrum is actually two lines. In the CW spectrum, there's two lines. You see one is a low field line, which links these two manifolds and actually corresponds to a nuclear spin transition, though, which here is assisted, whose dipole moment is hugely enhanced because of entanglement with the electron degree of freedom down here. And at the same frequency, though, you see a high field transition, which is the classic electron spin resonance transition, which just simply goes from an Z equals minus a half state to an Z equals plus a half state. And so in this regime, actually, you can then actually enhance what amounts to what becomes a nuclear transition. So if you wish, you could start off with a system in this field, high field range, actually round the external field down, and then actually mix that state with the electrons and then do a transition to the other manifold, and then come back up again. Okay, so how does all this work? And basically, this mixing of the nuclei with the electrons allows us to do much faster control, and actually allows us to see Rabi fringes now, again, on the time axis here with realistic powers and cavities on the scale of nanoseconds. Before I showed you a pulse, an RF pulse, which lasted a very, very long time. You see this RF pulse here. 150 microseconds long. Now we're doing microwave pulses, which are nanoseconds long, to have the same level of control over the nuclei. This actually down here shows you the Fourier transform of these Rabi fringes. For the two transitions, so the one predominantly electronic. So this high field transition is predominantly electronic, which is the red one, and the low field transition manipulates the nuclei as well as the electrons. Okay, so that gives you some idea of the degree of control and the remarkable long decoherence times that we have for deep impurity spins and so on. So that's very promising. So now what about the orbitals? Can we control those as well? Of course, the answer is yes. I showed you just the first part of your atomic physics course a few minutes ago. The second part, of course, was dealt with the fact that your impurities have, of course, not just ground state and the ionization energies of ruthenium. They also have a series of excited states, which are generally called Rydberg states. And the only difference with conventional atoms, again, is that I'm dealing with a cubic vacuum, not a spherically symmetric vacuum. So my Rydberg series, of course, is split by the cubic anisotropy. And even actually when S state is split. split. So all of these states are split. But apart from that, things are very similar to what happens in conventional atomic physics. There's one, and what I'm just showing you here on the right are actually the wave functions. Again, the 1s wave function embedded in silicon, and then the 2p wave function, excited state also embedded in silicon. The principal quantum number squared gives you the size of the nth Ripper state. And so if the 1s wave function looked big, the 2p wave function is way bigger. So this is 100 angstroms. So this is really now well within the range of gates, increasingly conventional gates in transistors. So, you might ask, how do we know that that picture is correct? And the reason we know that that picture is correct is from work done in the last 20, 30 years. This is particularly pioneering work done by William Thomas and Boris Rice, Robin Buck at Bell Labs. And if you went down to low, this is with phosphorus. So if you put phosphorus into silicon at low concentrations, you actually see a reverse series. You see a series of excitations, and then, of course, you see a continuum when you ionize the ionization energy of impurities. As you increase the density of impurities, you, of course, all know that there's a metal insulator, there's an insulator to metal transition. But that insulated metal transition, where that occurs, is defined by the radius of the impurities. So it's roughly inverse. Roughly, that density is an inverse proportion to the radius cubed. Now, of course, I just said that if I go to these higher lying quantum states, those states should become delocalized before the 1s states get delocalized, because those wave functions are bigger, and indeed you see that. So as I increase the concentration, even though my optical conductivity is zero at low frequencies, these Rydberg lines actually get spread out and eventually disappear completely, and then I have what's called a mobility edge here rather than some kind of a identifiable Rydberg line. And the fact, of course, that these mobility edge occurs long before I see the insulator to metal transition in the DC resistance measurement says that the excited wave functions are good. So this is where this field sort of was until essentially we came along a few years ago and realized that we can start to do some of the same types of physics that I showed with spin, and also some of the same types of physics that the atomic physics community have been doing with their orbital transition in their real vacuums with normal visible lasers. So the thought was, can we manipulate the orbital states the same way that we can manipulate spin using microwaves, or that the atomic physicists manipulate atoms using visible lasers? And for that, we actually needed a far infrared laser, which was tunable and pulsed. And actually, lasers in that terahertz regime are actually quite hard to come by. There's been a lot of progress in the last 20 years on various quantum cascade lasers, but they're actually not terribly flexible, and actually there are quite a few wavelengths where there is simply no strong emissions because of competition with phonons. Here's a free electron laser, which of course doesn't have any of those restrictions. It's just an electron accelerator, which puts an electron beam through an undulator, and there's the classic. And so the gain medium is actually simply the electron beam, which is basically passing through an undulator between two mirrors. Now, the FEL that we're using is a rather modest thing compared to the one that Ian uses. It's fit in a room maybe slightly larger than this, because we're not trying to get to kilovolt X-rays. We're trying just to get to terahertz photons. And what the accelerator produces at the end, through its undulator, is a series of light pulses, which look like combs. These combs are called macropulses. The macropulses consist of transfer limited micropulses whose length, and by that I mean that if we change the length of this pulse, the frequency width changes in precise inverse proportion to the time length of the pulse. Okay, so I can actually dial in whatever bandwidth I like, and then I get the pulse width basically that goes with it just from Fourier transforming. These micropulses, and of course the headway between the micropulses in the macropulse can also be changed between Fourier 1 and this is the characteristics of Fourier. It's a coherent beam, also which actually will be important in a minute. But first, I'm not going to take advantage of that coherence. We're just going to do simple bleaching experiment, pump probe experiment to measure T1. And so, again, we start the system here in not a spin down state or spin up state, but in a 1s state. We then apply a strong pulse to put it into 2p state. And then the system will be there, and eventually it will decay. And the way we monitor that decay is we measure the sample transmission to a weak probe beam. Of course, if the sample has, if the system has undergone an inversion, in other words, if I put all of the states, basically all of these atoms into this upper state, then if I come with a subsequent photon, as long as there's no higher lying state that I can go to which absorbs a lot, the sample absorption will have gone down a lot. I showed you Gordon Thomas's data, infrared absorption data a minute ago, which showed that there were strong absorption lines at these 1s to 2p transitions. If, of course, I use light to simply empty the ground state, I no longer can make those transitions, so the system now becomes, or the sample becomes transparent. It's black and then it's transparent. Of course, to monitor how it returns to the ground state, I simply watch for the restoration of blackness. That's how the pump probe experiment works. That's how it works in practice, with a variety of optical elements, as well as detectors and computer control it all. The main thing that we're doing here is just simply varying flight paths to vary timescales. It turns out that these kinds of energies are, by stroke of luck, extremely well matched to delay lines, because light actually, and this is defense for the English system of measures, actually light travels 1 foot in a nanosecond. And the time scales here that we're dealing with sort of they correspond to terahertz radiation, measured in picoseconds. And of course, 1/1000th of a foot is something that's extremely easy to measure just at an optical range. So it's possible to do a lot of very nice experiments, actually, relatively simply. So here's the design, basically, the schematic for the optics. This is what the optics looks like in practice. It's just an optical bench, but because we're dealing with a frequency range with a lot of absorption lines in the atmosphere of the Earth, we have to pump out the chambers or essentially backfill with some inert gas to keep the other gases out from causing problems. Again, it looks like any other optical setup. So here is this transmission experiment. So this is the lane between the pump and the probe pulses. This is the probe transmission. And this is logarithmic. You can see that, as promised, if I go to higher and higher power, and in this case what I'm labeling the data as simply the energy contained in one of these picosecond pulses coming out of the FPL. You see, as the energy goes up, the sample becomes more and more transparent, and then the opacity gets recovered on basically along an exponential function with the decay time of something like 0.3 seconds. So this actually is a very simple direct measure of T1 for this quantum system, where we just look at the two levels of one of the 1s levels and one of the 2p levels. Now, what causes so that decay time corresponds to a Q of something like 2,000 if I divide the decay time by the periodicity of the electromagnetic oscillation corresponding to the 1s to 2p transition, which is at around 40 millivolts. So what causes that decay? Well, we of course suspect that it's phonons, but how do we show that? What we did was we actually decided to look at a large number of impurities and also look at a large number of transitions between the Rydberg states of various impurities. And this actually shows you a zoo of wave functions that we calculated for all of these impurities. The donors are in blue, and the acceptors here are in red. So you can get some very strange, very large wave functions for these states. And if we look at both donors and acceptors, we can repeat the experiment over and over again. Sometimes the data look a little bit different. There's actually multiple time decays that you see, and you understand where they come from. But at the end of the day, you can look at all of the decay times and plot them against the phonon density of states at the energy corresponding to the transition line that's being studied for the particular impurity. There's a remarkable simplification of the whole problem, which you see when you plot this way. You see that actually all of the acceptors lie pretty much in the same straight line, and all of the donors lie in the same straight line with a slope which is almost exactly a factor for less, because this is a log plot. So it looks like the only thing that controls the decay rates, and therefore the matrix elements that control the decay rates, is in fact, the only thing that controls the decay rates is the phonon density states, which means that the matrix elements and degeneracy factors out in front are in fact all the same, except for the factor of 4 difference between donors and acceptors. And this sort of makes sense because why does none of the detail matter here? The reason that none of the detail matters here is that wave functions are so big, and so you're actually averaging over large volume of crystal. And so this is an interesting finding. It also says that to somewhat engineer longer decay times, we have to do something about the phonon density states. But once the wave functions get this big, there's not much we can do about the matrix elements. We can only play for this density states. Now, what about coherent orbital control? Can we construct coherent superpositions of, let's say, 1s and 2p states? Same way the atomic physicists can. The same way that we can construct coherent superpositions of alpha band spin states like magnetic resonance. And it's actually not obvious because when you think about it, creating and maintaining such coherent superpositions means moving charge around, and actually moving charge by fairly large distances in a real material, which is silicon. So it's by no means obvious that you'll have any kind of a sensible two-tone coming out. And what we've done here is we've just simply now relabeled the Bloch sphere, not with spin degrees of freedom, but with a pseudo-spin degree of freedom, which just represents the amplitude of the 1s wave function and the amplitude of the 2p wave. And the experiment, though, the end is then done in exactly the same way as the EPR experiment. It's the pump probe experiment. We put on a pump with a certain amplitude, and then we put on, after we let the system, we put the system down to the equator, and of course then it starts to dephase. But after a while we impose this rephasing pulse, which flips it around. Continues to dephase in the same direction that it started out with, but because I reverse the pulse, I eventually get essentially a refocused pulse at precisely the time t tau e were separated the pump from the rephasing pulse. So does this experiment work? Well, this is how the experiment was set up. And there's a very crucial thing with this experiment, and here we take advantage of the coherence of the laser, is we actually look at the system. Of course, at the end of the day, we have to detect photons somehow. And but what we do is we detect photons interferometrically. We produce, actually, the three beams that are required for the experiment, which is the initial pump pulse, then the rephasing pulse K2. The sample produces the third pulse, which is the echo. That's what we hope. But we keep a fourth beam, which is simply a copy of the incident beam. And we detect, essentially, using our slow detector, we can detect interferometrically these fast signals coming from the sample. And in fact, all detection occurs via interference. The next few will occur by interference between a copy of the initial beam and the various beams K1, K2, and Ke. And so the raw data, and so everything then happens essentially by measuring interferograms, where I vary these the positions of these delay stages.
So, these two state actually not only the silicon state, also the photon involved.
There's a photon involved, yeah. So I'm bringing the photon in. So there's photons from. There's two sets of photons coming in, and then there's no photons. And after a while, there's an echo that comes out. And so what I'm showing you here is the raw data, which is the raw interferograms between the pump rephasing and echo beams and the reference beam, which is a copy of the initial pump. Okay, so these are interferograms, and actually we've recently been looking at detailed coherence properties. But the bottom line is here's the pump beam interfering with the reference beam, phasing beam. These are nice sharp pulses. And then there's the echo. This appears, of course, long after anything else has come out. Comes to the sample. Here you see the actual echo pulse emerging from the sample, and it emerges at precisely the mean time, is precisely equal to the time difference between the pump and the phasing pulse. To make this look more familiar to people who do EPR and just like to look at the output on their screen, you can rectify these interferograms and get a nice pump pulse, rephasing pulse, and an echo pulse. Sanity check is, of course, to see that it's a real echo by varying the pump rephasing delay. You can check when the echo rephasing delay, when essentially the echo appears as a straight line with a slope unity. You can then go ahead and measure the decay, the Hahn echo decay rate, the T2 time, and that's shown here. This is the echo power as a function of time. And you can see here that there's a decay time, sort of a 1 over E decay time of over 6 picoseconds. Of course, you get to double this because this is power. So actually, you get to double that. So you have a T2 time of something in excess of 100 picoseconds. Last but not least, you can go and look for Rabi oscillations. And you've seen one. You can see this is what you should have seen. Of course, everything here we can do in absolute units. So we can measure the intensities in absolute units. And because we know the dipole matrix element exactly, actually we are actually able to produce a calibrated prediction for what the Rabi oscillations should look like. They should look like this dashed line. But after you put various imperfections in, most notably the fact that actually the beam intensity is of course distributed, the spot size is distributed in the Gaussian fashion over the spot size. That's the biggest correction here. You actually attenuate the further Rabi oscillations that you might expect. There's other factors that come in attenuating these, not just the fact that the spot size is finite. There's of course 2 photon processes which are not there in the conventional model. This shows at the end the comparison now of hydrogen and phosphorus silicon. You see the dipole, here's hydrogen, here's phosphorus and silicon. Here are the T1 times, and the T1 time actually for phosphorus and silicon is actually 200 picoseconds, which is only a factor of 8 smaller than the T1 time here. However, the Q factor, of course, has this 70 millivolts in the denominator. So the Q factor here is 1,000. Of course, here it's more like 100,000, almost a million. Nonetheless, it's quite respectable. We have competing decay processes here, phonons, rather than just dipole, which compete and add to the dipole decay. But in any case, phosphorus and silicon is an extremely good ion. Okay.
What sort of doping levels do you use?
These are typically 10 to 15%. But we could, of course, that's a degree of freedom.
So the same result from Gordon Thomas would apply where if you get up to 10 to the 18, you would see.
Well, then you see that the impurities start talking to each other, and that's, of course, where the computation comes in. Okay, so let me now move on to, I've shown you now orbital manipulation using photons. Let me now show you that we can manipulate orbitals of impurities using electric field. Here, what we've done is we've used, actually, the impurities have not been subsurface impurities, they've been defects at the surface. In fact, the defects that we've chosen to use are hydrogen vacancies in a hydrogen passivated silicon 100 surface. The reason we do that is these vacancies we can actually control, and we can build controlled structures of such vacancies. And the way we build controlled structures is actually by STM lithography. You start off with the surface, and then you bring in actually a scan probe tip, and you simply remove these terminating hydrogens. And with this, you can make all kinds of patterns of vacancies. And just to show you sort of a very simple case, let's say I start with a single vanillin bond on a hydrogen terminated surface. And then I can actually bring in my tip, and I can keep actually raising the sample bias, and eventually, there we are, add a second hydrogen. So now I actually add a second vacancy. So now I have essentially, if you wish, an anti-hydrogen molecule. So I have this artificial molecule, which has actually two of these defects associated with it. And I can investigate, of course, the wave functions of this object, again, using STM. And this is, here I'm showing you filled state topography and empty state topography. And what's interesting, actually, rather amazing, is as I change the current, like if I go from high current to low current on the STM, the shape changes of my empty state topography. Here I see the two hydrogen atoms, just as I did in the filled state. Just the orbitals here. If I go to lower current, actually, I see this big bright object in the middle. And just to show you the movie here, it shows us what happens essentially as a function. This is a series of images, basically with plus 2 volts. And what I'm doing here is just changing the tunneling current from 5 to 95 picoamperes. And you can see how this thing in the middle appears. Of course, there's no future over there. So this actually shows this now demands some kind of an explanation. And the explanation for this actually, again, comes from very simple quantum mechanics. I start off with a system here with a certain at a certain potential, and I have my I have electrons, basically filled states down here at the bottom of these, somewhere in these wells. If I do something to change the potential, I can of course see excited states like that. And of course, what I'm doing when I'm moving the tip, as I did here, basically back as I reduce the current, is of course I'm changing the band bending, and I'm therefore changing the potential that's seen by these electrons that live within this well. And so I'm mixing these states with these states to produce this kind of an image. So here I'm actually controlling orbitals now, not with light, but I'm controlling orbitals directly, simply with the potential that's generated by the variation in band bending as I move the tip back and forth. And so this again shows more rigorously, we've actually modeled these potentials, and they actually give a very good account of what's seen. Just to emphasize again what's going on. Of course, I can see these effects not just by changing the tunneling current, but also just simply changing the bias voltage. And what's shown here is a case where I'm looking at these states at the surface by changing the distance, this fashion, or by changing the bias. Now I'm in business, actually. I can start to construct all kinds of devices, or if you wish, or constructs, artificial molecules on the surface. I look here at 5 of these vacancies. And here I'm showing how, as a function of potential, the current wave function that's observed in that quantum well, just this one-dimensional quantum well, at the surface of silicon changes. So this is a chain of 5. And again, here are the line profiles through those images. And we've done simulations to look at the bound states in that type of a potential well, and we get a really good understanding of what's happening there. So here again, I have essentially artificial one-dimensional solid, if you wish, which I'm building by hand, building essentially one atom at a time on silicon, where I can tune the quantum orbits that are seen. There's a chain of 6. We can also go into 2 dimensions, this fashion, and 2-dimensional arrangement of these dangling bonds, and I can control them essentially again in exactly the same way by varying again the current or by varying the voltage. And I can do simulations where I can model these two-dimensional arrangements. Here I'm showing how I model them in 1D before, just by looking at basically symmetric and anti-symmetric combinations of ground state wave functions. 2D things become richer. I mix Px and Py and S states together to form things actually that actually don't quite now match some of the floral patterns that we had, but are getting reasonably close. So what we're doing here is we're doing two things. We're doing lithography at the atom scale to produce such new types of quantum objects on essentially the world's favorite material. At the same time, we're controlling the quantum states now with the potential. I would say this is essentially the semiconductor analog of the quantum corral Capricorn of Ibert. This is scattering, and these are actually quantum defects. These are bound states. So here we're constructing basically states one atomic orbital at a time. And here, what Ibert was doing was looking at scattering centers. What are we going to do with these capabilities? Well, once we have these capabilities, and actually, or we have these capabilities now, we're now able to start thinking of more elaborate constructs, including what I showed you was constructs with 2 impurities, 5 impurities of the same kind. We could think of going to constructs of different types of impurities. And the particular one that we find interesting is a construct involving, say, a deeper level and a shallow level like phosphorus. A deep level like bismuth, a shallow level like phosphorus. And here, being able to control the orbital actually can lead to control of magnetism, and not magnetism at a single site, but in fact, magnetism, the exchange interaction between spins on different sites. And just to show very simply how this works, or we hope it will work, is let's say we have a phosphorus atom here between 2 bismuth atoms. And I bring in, let's say, a photon, or I bring in some kind of a suitable electrical contact. I could take that phosphorus atom to an excited state in its well. Okay, now that excited state here, this 2p state, of course, has overlap with the 2p states on the bismuth atoms, and therefore, actually, these spins on these 2 bismuth atoms will therefore start to talk to each other. So actually, I can induce, basically, have a switchable, and since I can produce this coherently switchable exchange interaction between these two the spins on the 2 bismuth atoms. So orbital control is leading to control of magnetism in this way, in which I basically illustrated for the simple defects on the hydrogen terminated 100 surface. So, just to finish, so what we can imagine then doing is, let's say I have 2 bismuth atoms in a relative ferromagnetic condition. I bring in photon and basically coherently excite this P shell. I leave the system behind relative atom ferromagnetic state. And what this requires, of course, to do in the future is putting these individual qubits and individual control atoms in control location. And for that, we do actually simply use the hydrogen-terminated lithography that I showed you a minute ago and go one step further and bring in phosphine after we put the vacancies in. Actually, when you bring in phosphine, it attracts the silicon only at the place where the hydrogen atoms are missing. And so therefore I can actually make phosphine structures which are essentially copies of the hydrogen vacancy structures that I showed you a few minutes ago. Those copies of those structures then, the phosphorus now, can be buried or encapsulated essentially with more silicon, and the devices can then be contacted using various methods. We can integrate it perhaps with optics, and leaving us with very different looking paradigm for future integrated circuits than we have today, but perhaps one which might take us through the next sort of transition point in information technology. So, let me summarize. I think actually we will soon be at the end of the road for conventional silicon IT just for this reason. However, I think we can move ahead with information process not using sort of moving charges, but static charges with quantum spin and orbital degrees of freedom. And I've shown you a lot of the physics today. I've shown you some of the lithographic approaches. And so my conclusion is that silicon might actually well represent the future as well as the past. 20th century we had control of charge, and the 21st century we'll be controlling spin and orbital. Thank you very much.
Thank you, Gabriel. We have time, let's say, for a couple of questions.
Thank you for a very interesting talk, and not from this field. When in traditional MRI and NMR, we look for echoes from an example of atom. Are you looking for echoes from just one?
Well, you can't see one atom doesn't make an echo.
So
these are all sample measures, but Rabi oscillations, of course, you have.
So in this case, how do you control the quantum coherence between these atoms that are in different locations if you want to?
Well, you control them. Well, you control them in exact. I mean, you still apply control pulses. It's just the detection which is different. So the whole thing is you apply. So the control itself does not rely on the So what you have is you have a set of individual spins, and then people now are doing experiments like this actually in Australia with essentially coupling individual impurities to single electron transistors to measure the spin state on those impurities. And then what you do is you repeat the experiment many times over.
So wouldn't the lattice vibration decohere the atom?
Well, that's the point. The point is that the lattice vibrations don't decohere the spins, but they do, and that's what I tried to convince you. They cause very significant decoherence of the orbits. And that stands to reason because the orbital transitions involve moving charge around. Of course, lattice vibrations involve moving charge around by largish distances, as we do that. Inevitably means that the phonons matter a lot more here than they matter, let's say, at the base of the spins. But it's remarkable that we're still dealing with Qs of order 1,000 to 2,000, so even with these large motions and changes.
Okay, one more question.
Again, just off the cuff, one of the other things that we teach in solid-state physics is that if you start playing with acceptor states and holes, everything is exactly reversed and identical. But I suspect that is not true.
It is absolutely not true because, of course, the band structure of silicon is not invertible that way. It's actually very different. Acceptors are heavy holes and black holes and valleys. The band structure of silicon is certainly not whole electron symmetric. So the electrons are the degeneracies are different. The fact that the degeneracy factors is different degeneracy factors.
But is it meaningful to talk about whole spins in the same language at all?
Yes, it's actually that's one interesting conclusion that we came to is that the phenomenology is exactly the same.
Okay. Due to time, I am the chairman. I can get to ask the last question very quickly. Suppose you have many of these bismuths nearby. Will the giant nuclear spin of the nearby bismuths kill your T2?
Well, the giant nuclear spin, if you control it, of course, won't. And the other thing is, of course, nearby electron spins will do far more damage than nearby Because at the end of the day, the dipole moment is still a lot smaller. Magnetic dipole interactions with other bismuth spins is going to be much larger. Other electron spin is still much larger than that. And plus, at the end of the day, you really want to control all of the spins that you know about. And you'd like to remove all the ones that you might not know about, which are the ones that essentially from other isotopes.
Let's thank our speaker again. Since we started a bit early, I suggest we start 11:10. Is that okay? We have 20 minutes of coffee time, and we'll see you 11:10. Okay?